Hello, everyone. Thank you for attending today's session on commercial heat pump water heater field data. I'm Dolly COP with TRC, and I'll be your moderator for this session. First, we'll start with a few housekeeping announcements. First and foremost, we'd like to thank all our sponsors and ACEEE ally members for their support of the Hot Water Forum and ACEEE. Please use the chat box on the right-hand side of the screen to ask your questions of the presenters. Please refrain from using the chat for any dialogue other than asking questions. I'll gather all your questions and ask the presenters once all the presentations are complete. For questions that we don't get to, and to participate in the interactive discussion, please join us on the Zoom platform immediately following the session. The Zoom link is posted on the audience screen at the bottom of the page and also in the chat box to the right. And remember to use the passcode to get into the meeting room. Be sure to check out the tabs on the left-hand side of the app. We ask everyone to help us in our planning of future hot water forums by completing a conference evaluation. Anyone who completes the evaluation and includes a testimonial will receive a $25 discount off next year's hot water forum registration. All presentations will be available on demand for viewing to registered attendees on the Socio platform within a few days, and they will remain for viewing until May. Presenter slides can be found on their page in the program participants sections. And now, I'd like to introduce our distinguished panel of speakers. They are Doug Lindsay from Electric Power Research Institute, Al Tockley from Steffes, and John Bush from OTS Energy. We'll go ahead and get started with our first speaker. Doug Lindsay is a technical leader at the Electric Power Research Institute, where he has worked for 10 years. He leads the technology evaluation in the Customer Technology Research Program with active research projects on water heating, lighting, and appliances for the application of energy efficiency, demand flexibility, and efficient electrification. Doug will share field results from a one-year retrofit study in a McDonald's restaurant with a 120-gallon integrated heat pump water heater and present valuable insights into system design, sizing, operational issues, and performance. It's great to see a restaurant field study back at the forum. And take it away, Doug.
All right, thank you, Amin. Let me pull this up here. All right, so as he said, my name is Doug Lindsay. Happy to be here today to talk to you all about a field demonstration that we've hosted over the past little bit over a year now. As he mentioned, I work for the Electric Power Research Institute. Just a brief background on EPRI. We are a nonprofit independent research organization, primarily funded by electric utilities. We are an independent organization, though. We don't certify or advertise for any specific manufacturer or anything like that. We try to be as scientific and as real collaborative as we can be, providing thought leadership throughout a number of programs and issues throughout the electric industry. I work specifically in our technology, customer technologies program at EPRI, where we focus on residential, commercial product demonstration and evaluation, and even some development. So today I want to talk about this project that we did in partnership with Southern Company, and thanks to Southern Company for sponsoring this work, where we demonstrated a new integrated heat pump water heater for fast food application. I'll talk about the product a little bit more in more detail here in a second. But our main goals were to assess this technology for its efficiency and or electrification potential, looking at the product sizing, ease of installation, customer acceptance, and just energy performance in general over the course of 1 year, where we did some detailed monitoring on it. So here is the product that was selected, an A.O. Smith CHP 120. It is actually the only light commercial integrated heat pump water heater that I'm aware of. This was released in 2019, and our project demonstration actually began in 2020. But here's just a little bit about how it works, what the product looks like. You can see the heat pump and the evaporator fans are on the front of the storage tank, which is in the back. So it's a completely integrated system. You see the wraparound condenser on the tank. There are two electric resistance elements that serve as additional heating elements. So one on top, one on bottom. It is an R134A refrigerant product currently. You can see it's rated COP of 4.2. It has consumes about 3 kW on the heat pump side, and I'll show some more details into what we saw on the field. This product is rated for 208 or 240, and we actually ran this at 208 in the field. It's a little bit larger than some electric resistance or natural gas tank solutions because it has the additional heat pump. A little bit taller as well, and I'll comment a little bit on that as well in some of the pictures that we have. So like here's an example of some of the applications that we looked at in our site selection process. We actually were looking first at Sonic's restaurants and then transitioned to McDonald's. All of these were in southern Mississippi, and we had a great rep from Mississippi Power to go look at field sites for us during COVID. That was another challenge for this project. It's almost completely happened during COVID, so it was a little bit of a challenge to complete. But here's some examples of sites that we did not select. These are other McDonald's in the southern Mississippi region. A lot of these probably would have worked, but we picked one that would have been the easiest to do with the install. You notice in all of these, or in most of these, there is a washing machine almost directly next to the heat pump water heater. In this top left picture, that did limit us in terms of space constraints a little bit. You also notice that all of these are electric resistance water heaters. All the McDonald's in this region are actually all electric restaurants, and that is been that way, I think, for a long time. So we didn't have the electrical capacity constraints that several other areas of the country have to deal with when installing a heat pump water heater. So the site that we did end up with is this one on the right here. This is actually one of the older water heaters of all the ones that we looked at. It is also electric resistance, 80-gallon electric resistance water heater, 3-phase, has 6 3 kW elements. You'll notice here in the picture that it's right next to the back freezer, so it's kind of towards the back of the restaurant, but it's still in the kitchen space, and that's something that you may know as a good benefit of heat pump water heaters in a hot application like a restaurant kitchen. They can definitely use the beneficial cooling, and that was one of our primary objectives as well, to get this into an application where it would make the most sense. You can see this is a picture during installation of our monitoring system. So we did do 1 week of baseline monitoring before we put in the heat pump water heater, and I'll show that slide next. But we did get a comment, interestingly enough, from one of the store managers about it not providing enough hot water all the time. They would often have to delay a dishwashing cycle by 30 minutes or an hour just to let the tank recharge. That was not something that the facility manager knew when he arrived. That was kind of a new learning once we got into this site. So we were happy to come into this site and hopefully provide a better water heating solution. So yeah, as I mentioned, there were several actually resistance elements that weren't working, and that was not known until we got into this project. So looking briefly at the week of baseline testing that we did, my chart showing at the top the water flow in 1 minute data intervals. So we measured the water flow of inlet to the water heater. We measured the electrical power consumption, which is based on voltage and current. We measured the inlet and outlet water temperatures. We measured the ambient air temperature. And then once we got the heat pump installed, we measured the intake and supply air temperatures as well. So pretty detailed monitoring, all at 1 minute intervals. And as you can see in this picture, there's a lot of water draws throughout the day. Almost constantly, there's some amount of water being pulled through the water heater. And my red dots here at the bottom are showing there are some instances where the outlet temperature did drop significantly below set point of 140. But it's generally pretty quick and was able to recharge. But that was just in 1 week time that we saw several instances of a little bit of underperformance. So here is the installation that we put in as part of the project. The project paid for the product and installation. You'll notice the heat pump water heater here on this left picture. We actually did have to knock out the concrete base to get the product to fit into this space because there was some pipes going through the back of the wall that we needed to not have to move. We probably could have moved them if we had to, but wanted to keep the installation as cost effective as possible. And you can see some of our monitoring equipment. We've got the air temperatures here. We've got our water flow meter here. There is a condensate drain that was already existing. That was another benefit to this location here as well. Here you can see that the unit has a touch screen. It does have on the front display tank temperature, set point temperature, what's the status, time, and there's a menu. You can go through more options there. And I'll comment a little bit about this tank temperature setting a little bit later. So let's get into some of the data. So after over a year of testing, we've compiled some summary charts here. This first one on the left is an hourly load profile. If you're not familiar with a chart like this, it is an average of each hour throughout the entire project over the course of 1 day. So we're seeing here blue is the gallons consumed at each hour of the day, and orange is the average power during each hour of the day. And it is showing here at the highest water consumption on average was right in the middle of the day, right at lunchtime is when we saw the most water being drawn, but it's also when we saw the most power being drawn. And if you're not familiar with the chart like this, usually when there's power and gallons overlapping or intersecting, that generally represents electric resistance operation. And so when we see separation from the gallons and the power, like here in the mid-morning and the early afternoon, that generally indicates heat pump operation. So one thing you can learn from this is that the electric resistance elements were used pretty frequently in the morning, at lunchtime, and in the nighttime cleaning. And I'll show some examples of that in more detail in a little bit. 420 gallons of hot water usage per day is our average that we saw throughout this project, and about 42.5 kW per day. On the right, I'm showing a separation of breakdown by weekday, or day of the week, to see if there was any difference in terms of the water draw profile throughout the week. So we got really detailed water draw profiles. This restaurant, you can actually see in this area right here, it was open 24 hours on Friday, Saturday, and Sunday. Whereas Monday through Thursday, it was not open 24 hours. And so you don't see any cleaning happening for a few hours when it did close. But generally, we saw pretty similar load profiles no matter the day. Some other small differences. You can see the weekend had a little bit more water consumption on the weekends, like Friday and Saturday and Sunday. But generally, pretty similar throughout the whole year. So I mentioned 420 gallons being the average of the water consumption, but the scatter plot actually shows daily COP that we calculated versus daily water drawn through the tank. And it's a wide range. You can see from 250 up to 700, various days, various water draw schedules. I didn't mention this earlier. I guess a lot of the loads in this restaurant are the dishwasher, the hand sprayer to clean off dishes before they're put in the washer. There are some hand sinks connected to the bathroom as well, and a mop sink. So those are the primary hot water users in this restaurant. But looking at the COP trends, you can see that it ranged as well from 1.5 all the way up to 2.8. That 2.8 number is a little bit of an outlier. And I looked specifically at this day. This was actually the day where we didn't have any electric resistance usage, whereas the rest of these days did have electric resistance operation mixed in with the heat pump operation. So a real hybrid solution is being shown here. We calculated an average daily COP of 1.9. But as you can see, it varies significantly day to day. Some of my theories of why this would be is maybe you have different people working on each days. Maybe you have people that accidentally leave a faucet on for a longer period of time. But generally, the COP is very dependent upon when the water is being drawn and how long it's being drawn. So if you have a lot of short draws that are spread out, you're more likely to see the heat pump be able to recover based on the settings that the manufacturer has in place. But when there's a long or drawn out uh, water draw, then the electric resistance elements do kick on. And so I can show that in a little bit more detail here in this example day that we have, where there's 476 gallons drawn. And I picked a day that was right at our average of 1.9. So you get a good feel of what an average day looked like. And you can see this was, I think it was a weekend where there was water drawn all throughout the day, even in the early morning. But there are several instances of the electric resistance elements kicking on. So we have examples here of 2.7 to 3.5 kW for the heat pump operation alone. And you can see that it kicks on several times throughout the day. But there are several instances as well of the electric resistance backup elements kicking on. You might remember I said that there's two 6 kW elements, but since we're operating at 208, we actually saw a little bit less power consumption from the elements. So that's why our max kW was around 12 kW. But you can see even when these backup elements are on, the heat pump is still on. It's kind of hard to see here, but it is operating at the same time as these elements. And you can also see two tiers. So the bottom element and the top element are on at the same time here. But that's not always the case. Sometimes only one element is on. I'm showing the outlet temperature here on the bottom as well, just to show that we did deliver hot water throughout the project. And we actually had the users increase their set point from 140 to 145. And I'll talk about a little bit why they did that here in a second. But overall, we saw good performance throughout the project. Here's a look at the air and water temperatures that we measured as well. I'm going to focus first on the bottom graph, which is the inlet water temperature to the tank. And these are daily averages, but you can see a large change in the inlet water temperature throughout the year. As I said, this is in southern Mississippi, but got down in the 50s for a little while, not very many days. It was down in the 50s, but it did get up pretty hot, above 80 for the summer pretty much, all the way up to almost 85, 86 degrees on the inlet water side. Measuring the air temperature, we measured this at several different points. The blue line is actually upper room ambient air temperature, where we measured it at our data acquisition box, a little bit separated from the water heater itself. Then we're also measuring in purple the intake air temperature and the exhaust from the front of the unit itself. And you can see that it was significantly lower at the exhaust throughout the day from the top of the room. So it's really a localized temperature change when we saw the heat pump in operation. And it's also surprising, it was a little surprising to me to actually see the restaurant be as cool as it was at the upper room ambient temperature throughout the entire year. I expected it to get a little bit hotter in there. But we had found out from the facility manager that they did have a few years ago, they installed additional air conditioning specifically for the kitchen because it was very hot there. So maybe if we had got to this site a little bit early, maybe we could have helped to offset some of those AC upgrades. But also, depending on where you have the heat pump water heater in relation to the workers in the kitchen, this was kind of a little bit in the back corner. So the cooling wasn't as beneficial, but the workers still did very much appreciate it during the summer that it was very cool by the water heater. We did have a few hiccups along the way, as all field projects go. There's some things that don't go the way that you expect them to. But we did have some compressor fuse problems throughout the project, specifically early on in the project where the heat pump would stop operating, but the electric resistance continued to operate. So actually the restaurant never really noticed. I noticed this based on my data acquisition, but we had the heat pump go out several times because of a fuse blowing. And we worked with A.O. Smith to find the solution, and we got that changed out, and we're able to resolve that problem. And hopefully that continues to be a good solution going forward for us and for all of their future products as well. We did notice that the fans in the evaporator coil did get very dirty. Restaurants are a very dirty environment. There's a lot of grease in the air. We did not have an air filter on the heat pump water heater when we started, but we have since added one. A.O. Smith informed us they had a retrofit air filter kit, and I am of the understanding that that's going to be something that becomes standard on their next generation of this product line. But so we've added the air filter kit to hope to keep the evaporator coil and the fans from getting as dirty, but they might still require occasional cleaning. And then, as I alluded to a little bit earlier about the average tank temperature display on the front, we actually found that the customer perceived this as the outlet temperature, which it is not. When I was there on a site visit, I actually watched that number change from 140 to 120 very quickly during some dishwashing cycle. And I knew that was the average tank temperature, but based on comments from some of the facility manager and the store operators, that they had perceived that they were getting 120-degree water at their dishwasher. And that's kind of why they bumped up the tank temperature at the beginning of the project. But my data shows that they have not been getting anywhere near 120-degree water during that time. So I think it's just a misunderstanding of what that number represents. If it was me, I would either bury that number where it's not displayed prominently on the front menu, maybe something you have to click through, or just display the outlet water temperature. But that might not be something that is being monitored by the tank. So that's just a piece of advice for me, that it was a little bit confusing for the customer, as they thought that it was underperforming when it actually was not. So in conclusion, I just want to wrap up and say that we had a really good demonstration overall. We estimated yearly water heating savings close to 12,000 kWh. I don't have it shown here. I have it in our report for Southern Company, but we're estimating probably a 3 to 5 year payback in this application. It's because we're seeing double the efficiency of what the standard electric resistance product would use. So with the average COP of 1.9 and the water draws of around 420 gallons per day, this is a really good product for this application to get more efficient water heating into these spaces. And it's a plug-and-play solution. It's integrated. There's not really any design necessary. Just got to make sure you've got the electrical capacity and the space to put the water heater in. And it was a really easy solution to get into this restaurant, actually. And the positive thing here, I have my last bullet, is that the facility manager is actually considering purchase one on their own dollar to put in one of their other sites where they had a water heater that was about to fail. So to me, that's a positive, to see that the store had a good experience and that they want to use an efficient product and they understood the benefits of it, and we're excited about the technology. So that is all I have. I'll wrap up there and hand it back to Amin. Thank you.
Thank you, Doug. That was really interesting. Actually, commenting on your results of daily hot water use and the variations from day to day, those are very consistent with past field studies in quick service restaurants. So yeah, definitely behavioral. And also just some days you have a heavy day of usage, a lot of foot traffic, and other times you don't. So that was great stuff. Yeah.
Thank you.
Yeah, so our next speaker is Al Tockley. He's a product manager for Steffes, a manufacturing company based in Dickinson, North Dakota. And he has over 30 years of experience focused on electric thermal storage and demand response technologies to meet sustainable electricity distribution and decarbonization goals. Co-presenting is John Bush. He's president of OTS Energy, an engineering consulting company based in Knoxville, Tennessee. John is a mechanical engineer with 14 years of experience focused on research and development and helping deploy efficient heat pump technologies. Al and John will share field performance results from a recently completed Bayview Tower project in Seattle. This building retrofit project was a partnership with Ecotope and Mitsubishi Electric. And I'm really excited for this presentation. So with that, I'll turn it over to you, Al and John.
Thanks, Amin. You want to go to the next slide, John? So we're going to look at an initial look at a real-world performance data of a larger package central heat pump water heater system. And I guess the big thing here is what we're trying to do is package the system up so that it becomes much more simple to get installation. We're looking at just 3 water lines and a single connection point for the electric to be able to, again, provide simple installations. Next slide. So some project details. Bayview Tower is in Seattle, Washington. The owner of the building is Seattle Housing Authority. We put it in July of 2021. It's a 100-unit low-income housing project, and kind of interesting about that is that we're really demonstrating how we can do energy efficiency and decarbonization projects in some of the underserved community. And we're targeting an efficiency so we can have a 59% energy reduction. Over on the right, you can see as the unit left our factory here in North Dakota, on our shuttle lift, we're putting it on the trailer to get sent off to Seattle. And our key takeaways are that the system is delivering expected results, and John will go through those. And we hope that people will consider central heat pump water heater systems for upcoming projects. Next slide. So it does take a team to get the system put together, and this is a project that was no different. Ecotope was a system designer and the project manager for the M&B. Mitsubishi Electric, Metis, Mitsubishi Train, donated the heat pump, the controls, some engineering resources, and the on-site install and startup labor. And of course, at Steffes, we built the package, and then we were also on site for the installation. And here you can see a picture of us at the startup, and we're on top of a mechanical room. This is outside, so the system was set there with a crane. Next slide. So some of the pieces, parts that were in the overall system. Of course, on the right-hand side, we show the Mitsubishi QAHV air-to-water heat pump. We have 3 tanks that are piped in parallel, and each tank we show 5 sensors there. So we're monitoring stratification. Of course, that's important, especially as you're doing load management kinds of things, to make sure that you're always delivering hot water off the tops of the tanks. Kind of in the middle, there's a isolation heat exchanger so that we aren't putting the actual potable water through the heat pump. That is a requirement of Mitsubishi, and one that we at Steffes think is a really good idea. We show a secondary water pump that pumps the water through the tank or through the heat exchanger and into the tanks. And then of course there's controls. And then number 1, which is kind of down in the middle there, that's the single connection where we bring in the line voltage for the system. Next slide. So this system it's a retrofit system, and so we had an existing mechanical room that had water heaters in it, and those were retained. and we use those as the temperature maintenance system, or known as the swing tanks, as the water is getting recirculated through the building. And then there were new electronic mixing valves that were also put into the system as well. John, on to you.
Thanks, Al. So hopefully everybody can hear me okay. We've had a little thunderstorm coming through overhead here. I think it's passed, but hopefully there won't be any background noise or a flash and a boom, and hopefully you won't get to see me jump out of my chair here. So I'm going to talk to the data collection, the data we've analyzed so far. I'm going to summarize what's on this slide, which is just an overview of the data collection, and then the details here, anyone who's looking through this stuff later on can look if you have any questions. So the building switched over from the existing electric resistance heaters to the heat pump in August. Data collection got up and running in October. And then we had a pump failure. We had to replace one of the pumps in the building in mid-December. So that was convenient for getting us some surprise, unexpected baselines data. But for today's presentation, I've got October to December data. System is back up and running, but we haven't analyzed the data since that reboot for presentation purposes. In the spirit of full disclosure, there are mode changes that happened during the period that we're looking at here. None of them have a huge impact, on big picture results here. So I'm going to sort of gloss past them for this presentation. And hopefully we're kind of hoping that this will be a part 1 of 2 presentations. So hopefully at next year's hot water forum, we can share a little bit more. So this slide is showing kind of the operating conditions the heat pump is exposed to. On the left, you can see the average, minimum, and maximum daily temperatures at the site. This is Seattle in the fall, so it's pretty mild weather. The orange is the city water temperature entering the building. You can use this data conveniently enough to go look at the manufacturer's performance data and calculate kind of our expected COPs at any given condition. Those expected COPs, those are the heat pump instantaneous COP, so delivered capacity divided by power, instantaneously. It doesn't include storage or anything like that. But based on the weather conditions, a rough range of about 2.4 to 3.0 is what we would expect. This is a CO2 heat pump, so delivering about 150 degree water into the primary tanks. On the right, we've got water draw information. The bottom right is the daily totals for water draw during the period we're looking at here. We had an average of 2872 gallons per day, and most days are within, about 10% of that. So there wasn't a huge variation at this site. A few outliers, of course. The upper right is the average water draw profile during the monitoring period. So, pretty typical draw profile for a multifamily type of building. This slide is showing a typical week of hot water usage. On the right, Al mentioned the 5 internal temperature sensors on each tank. You can see the ports here for them. So they're along the walls of the tanks, in between the caps here. So it captures, most but not all of the volume in the tanks. And each of those corresponds to a purple line here on my graph. So I'm showing the stratification. I'm only showing one of the 3 tanks, but they're in parallel. They stratify roughly the same, but that'd be a heck of a graph to try to look at with 15 of those lines instead of just 5. The red line is, if you can picture the water leaving the 3 in parallel and coming together to a single pipe leaving the system, that's that temperature there. So that's the merged temperature leaving the 3 parallel tanks. Green and yellow here are the mixing valve leaving and returning. There are 2 mixing valves. We averaged them again to make the graph easier to visualize here. And from this temperature data, this is a typical week in October. Pretty representative, though. You can see the discharging and charging as these temperatures in the tank, the thermocline moves down and up. You can see the bottom getting colder and warmer again. The nice thing is the top of the tank, the leaving temperature out of the tanks in parallel is always comfortably above that mixing valve temperature. It goes to the swing tanks and up to the mixing valve. So we're always delivering hot water on the order of about 20 degrees to 30 degrees higher than what's needed at the mixing valves out of the primary tanks through the swing tanks and out to the building. The bottom portion of this, the orange shows power and the blue shows the water draw profile and average GPM. So for a system like this, you'd be shooting for something like 10 or 20 hours of runtime per day on the end of 20 for like the design day, for example. You can see here we've got some nice long run times. Some days are shorter than others. Here we've got a relatively short one. And here we had a case where, in the overnight, the system had very, very nearly reached the turnoff threshold when the next morning's draws started up. So this is kind of interesting to look at. The draw, brings down the tanks, and then as we're reheating, we're kind of roughly in balance with the draw. So we're, you can see the temperatures kind of moving around, but staying about where they are and delivering hot water as we recharge. And then as these temperatures climb back up, we very nearly reach fully recharged, and then the next morning draw starts. And so the system keeps running and just kind of maintains, again, a nearly fully charged tank on this day. So this happens a few times in the data here, but we're seeing typical run times are around where we expect for the system, which is a good sign. That's sort of as designed, and we're meeting the draws on the building, without excessively long or too much short cycling or anything like that. So this next slide, I'm glad Doug went through what these average hourly profiles are, because now I'm going to show a few of them. So thank you, Doug. The left is the average profile for some temperatures and water flows. So the red is the same as from the previous graph. It's the temperature leaving the primary tanks is the average daily profile of that. So you can see during the overnight, when there hasn't been a lot of draw, the tanks are almost always fully charged. Hot water is leaving close to 155 or so. And then during the daytime, when we're in the process of recharging, the tank charge level might be a little bit lower, and we still have on the order of about 145 or so leaving into the swing tanks and from there out to the building. Mixing valve temperatures were nice and steady throughout the whole period here. The graph on the right, we have the heat pump average hourly power in orange and the swing tank elements power in blue. So the heat pump, you can see, and as that previous graph kind of showed, almost always is on during the daytime and into the evening. With a big system like this, that's heat pump recharging of big volume tanks, you kind of expect the heat pump power to lag a little bit behind the water draw. So the draw, drops down towards midnight, and the heat pump keeps running, and it shuts off sometime often after midnight or so. And what this low period here, the heat pump doesn't modulate down to 6 kW. What that is, again, it's an average. So it's sometimes it's on, sometimes it's off. So a lot of the time it's off around 5 a.m. Sometimes it's finishing up or just starting for the next day. The blue is showing the swing tank element power. A thing to remember on these swing tanks, they can act as the backup system. So if there were cold water coming out of the primary tanks, the swing tank elements can turn on to act as backup. But kind of their main job is reheating recirc water when there's not a lot of draw. So the swing tanks get hot water from the primary tanks on the way out to the building. And that's kind of the main way that the swing tank temperature is increased during the day. But then the sort of secondary possibility is the backup electric elements. And when that can happen when the draw is very low, so there's not a lot of hot water coming out of the primary tanks. And that's kind of what we see here. We have cases where the water draw is relatively low, and occasionally the swing tank elements kick on to make up for the recirc losses in those conditions. Again, that's sort of operating as designed. That's kind of what we expect to see in a system like this. This graph is sticking with, or this slide rather, is sticking with power and energy. The part on the left, this is each day as a stacked bar. So blue is the energy consumption of the heat pump water heater, and orange is the electric resistance heat. Kind of the big picture thing here, more than 90% of the energy consumption is heat pump. Less than 10 of the total is the electric elements in the swing tank, plus everything else, the pumps and so on. The average of this entire period here is 255 kWh per day. On the right, we have COP data. So blue is the COP of the primary system. That's the heat pump only. We're calculating that here based on hot water delivered out of the primary tanks. So energy delivered out of the primary tanks divided by the heat pump energy for that same time interval. So that is including some tank losses where the manufacturer's documentation is just the raw COP of the heat pump. So that range was 2.4 to 3.0. And what we're measuring here is 2.4. So that's encouraging to see that we're getting, with the storage for the primary tanks, we're getting, within that range of just the instantaneous heat pump COP. So that's a good sign. And then the system COP includes the energy consumption of the swing tanks and the pumps and so on and so on. And that one is 2.3. So again, not a huge impact to that overall system COP. Remember, this is Seattle in the fall, so kind of the poster child for mild weather, I think. We would expect a little bit lower in the depths of winter, a little bit higher COPs in the middle of the summer. And we're hoping that next year we'll be able to share some more of that type of information. Okay, last of my slides here before I switch back to Al. So I mentioned at the beginning we had one of the pumps on the system needed to be replaced, and Al mentioned that the swing tanks of the current system are the existing electric water heaters that were the main were the only water heating system for the building previously. So when we had to switch out that pump, we just, the system, some minor control changes, and the system went back to those baseline electric resistant tanks. And conveniently, surprisingly for us, we got some baseline data, which we weren't expecting. So here, this graph is courtesy of our friends at Ecotope here. This is the daily energy consumption of the heat pump alone, and then the total, again, adding up all the components here. So as I mentioned, this was 255 kWh a day was the average here. And then this is when the pump is replaced here. And so here's the total energy consumption in the post period here. And the average on that was 566 kWh per day. So this translates to a little over 300 kWh per day savings. It's a 100-unit house, so you can, or building rather, so you can do the math on the kWh per day with and without, and per unit that is. And it also the math on that works out to 55% energy savings with the heat pump operating compared to the baseline, which is encouraging. And with that, Al, I believe you're taking these last two.
So just to kind of reiterate what John was saying, system was operating with an overall COP of 3.5 during the fall in Seattle. We saw 55% energy savings over the electric resistance heat. We were targeting a 59%. So while we think that is pretty close, we are anxious to see how we're going to end up over a full year and not just in the fall. Hot water delivered at target temperatures throughout the monitoring period. Of course, anytime you're doing water heating, it's super important that you have hot water to the people that want hot water. You don't want to take that call, trust me. And the project is ongoing, and like John said, we expect to present more data next year with having all the seasons through that. And the lessons learned, factory testing and pre-commissioning can reduce plumber risk by proving system operation prior to arrival at the job site. In addition to the heat pump, ancillary items like secondary pump, mixing valve, system controls, remote reporting are critical in the success of a central heat pump water heater implementation. And things that we're going to consider in the future, and I saw this was one of the questions, is why do you use parallel instead of series? It is something that we are looking at. Our current systems that we're working on are actually use series instead of the parallel. But the idea of looking at both of those is to get the stratification to be the best and be able to maximize our storage, especially when we start doing load control, which, by the way, is starting this week at Bayview. Looking at different backup heat supply options. Some of the people we've been talking to are very concerned about it as we look at colder climates. And we've actually had people mention doing dual fuel kinds of systems. So it's something that we continue to evaluate. And we're looking at how can we have a package system, but still have flexibility to support as much system locations as possible. And again, thanks to our project partners, Mitsubishi Electric Train and Ecotope, and for all the help that went into this. We should mention BPA was also very much involved with all of this project as well. The picture on the right here, we show the inside of the housing. The Advanced Water Heating Initiative has lots of on-site kind of displays, and you can actually go in and do a virtual reality kind of tour of this. That's very exciting as well. And with that, we are done. Thank you. I guess we'll wait for any questions.
Thank you both. That was really informative. And congrats on having a successful and really complex retrofit project. Yeah, I look forward to hearing more about the all-season performance at the Bayview Tower project next year. So thanks again. Looks like we have roughly 10 minutes to answer some questions. And yeah, so perhaps since we just got finished with the second presentation, we can answer some questions directly off of that. And this is a question that came in from Jack towards the beginning of the presentation. It was for Al, and it was, why do you hook the tanks in parallel rather than in series?
So that was kind of something that we were trying to prove out. There's been a lot of systems that have done series in the past. One of the people that we were collaborating with was operating under an assumption that we could get better performance in terms of stratification going along with the parallel tanks. And John, maybe you can comment on how we think that's worked so far.
Yeah, great question. So this is one of the things I wish the third sort of, I wish our friends at Ecotope were on to talk to. There was a hypothesis sort of under test here about the use of parallel versus series. The tanks certainly do stratify, fairly nicely. One of the things we were looking out for is, whether the stratification could kind of get out of sync between them, and that doesn't seem to be a big issue here. I believe that one of the concerns that they were trying to address was, the instantaneous flow, like the minute by minute GPM here can be as low as 0, of course, and as high as I think on the order of 12 and 15 or so. And so I believe part of the intent of that was to try to lower the velocity of entering water per tank here. But as Al mentioned, we're certainly looking at series, and series is the kind of the predominant piping configuration out there in the industry too. So I hope that answers the question.
Yeah, I think maybe we can take that back to the Zoom call and kind of really get into that one. I'll move on to the next question. This is also a question for Al. The return piping to the heat exchanger should have been tied to the same header that is supplying the cold water to the tank. Pulling off what is supposed to be the drain line will introduce sediments into the heat exchanger that would normally settle out at the bottom of the tank.
Sure, and so as we look at our ongoing designs, there's a lot of thought going into how those returns, where we should be drawing. We obviously want to be drawing close to the bottom of the tank as possible, but we also are very cognizant about not inducing extra flow in the tank that would cause our stratification to go away. And so we are very much looking at that. And I agree 100% that we don't want to pull right off the bottom of the tank because there will be some sediment in there.
Great. Another question from Jack. How much do you think you would reduce the electric resistance usage if you lowered the set point of the swing tank at night?
I can touch that. I don't have a specific answer on how much lowering the set point would be. One thing to consider is if you imagine just a really long standby period, the loss rate into that tank is a function of the loss rate out in the pipes in the building. So if you have 10 kW of loss or whatever, then eventually over time you've got to make that up with 10 kW of input heat. Now, to Jack's question, if you have the tank itself sitting at a little bit higher temperature, there's going to be a little bit higher losses associated, out of the shell of the tank to the ambient. So that would increase that a little bit. But kind of the dominant thing there is the temperature out in the building loop. And I saw another question about the range of those, the swing tank portion of this and swing tank losses and energy. One thing to remember is a lot of the swing tank losses here are essentially being recovered or reheated by the water flowing out of the primary tank. So that 160-ish or 150-ish rather degree water flowing into the swing tank is reheating the swing tank. That makes up some of the losses. And then the other thing that's kind of interesting and very, very on our radar as we go through working with Stefas on this is how much those recirc losses can vary from building to building. We've kind of informally gone out and surveyed trying to figure out what that loss rate is. And Ecotope uses a watts per dwelling metric to try to estimate it. And we've heard the range on that losses per dwelling being as low as 50, so 100 units, 50 times 100, and as high as 400. So the range, and that obviously depends, how insulated are the pipes, and did you run them, through an ice box and over the roof and all that stuff to each unit, or are they short pipe runs, well insulated? So that there's a huge variation what those recirc losses actually are in practice, and so that's kind of a design challenge that is very much in the thinking going forwards.
Great, thanks, John. That's perfect. That covers all the questions for the second presentation, and we can go ahead and move on to some questions for Doug off the first presentation. Bob Barrett asks, don't most dishwashers have internal heating elements? And maybe before answering that, you can maybe, if it was a high temp dishwasher or low temp dishwasher, if it was an under counter, or if it was a door type, maybe that could help answer.
It was a door type, and I took a picture of it. I hadn't looked at it recently. See if I can find it quickly, but yeah, I'm not sure off the top of my head. Yeah, I'm not sure, but that's a good point. And I mean, you probably have a lot of knowledge on this space as well about what's typical in a restaurant application.
Yeah, it's I don't know what McDonald's spec is, but certainly some low temp dish machines, door types will have no internal heaters. Sometimes they will have a wash tank heater. Now, if it's a high temp machine, it could be even a heat recovery machine. Those units certainly have electric resistance heating elements. So just really depends. So kind of moving on. Another question from Jack. Can you set the electric resistance elements at a lower set point than the heat pump so that they don't come on all the time?
No, so that's not a configurable setting on this unit. That is something I guess A.O. Smith could consider in the future, but that is not a system setting. We left it in hybrid mode the whole time. We did not switch modes. We let once we set it in place, we let the user, the store manager, change whatever they wanted to, operate however they wanted to. They actually didn't change anything except for the set point early on in the project, and basically just let it run how it goes.
Awesome. Yeah. And we'll do one more question now and perhaps take it over to the Zoom. So the question is from Jack. It looks like the daily load profile is pretty predictable. Could you raise the set point a little higher just before the heavy water usage to preheat to be able to use more heat pump heat? So a little load shifting, I assume?
Yeah, that's an interesting idea. There was a mixing valve on this system, and I guess I should also answer the circulating pump question. There was not a circulating loop for this field site. The mixing valve, I think, was only for the hand sinks, or the pipes going towards the hand sinks. But this unit was not remotely configurable. So I know in the next iteration of this product that A.O. Smith is looking at adding demand response functionality. So that is a really good idea to try to preheat and then maybe even use a mixing valve to get some extra capacity with the heat pump before the large draw. So yeah, that's a good idea.
Excellent. Thank you. I would like to thank all our speakers for their presentations and to the attendees for participating in today's webcast. Again, if you'd like to continue exploring the presentations you've heard in this session today, please follow us to the Zoom chat room. I'm actually going to enter right now, and the link can be found at the very bottom of this page on this platform, or the Zoom link to the left. So please copy or note the passcode and to gain entry, and we can wrap up the session on Socio and see you all in the Zoom platform. Thanks, everyone.
Thank you.